Hello everyone, my name is Bora Derin from Istanbul Technical University, Metallurgical and Materials Engineering Department. Today I would like to talk about our research papers published in journals or proceedings, which we have conducted in collaboration with different research groups. My intention here is not to delve into the details of these studies, but rather to demonstrate how we utilize the FactSage for our thermochemical calculations. Our first case is about a very small project entitled Vacuum Oxynitrocarburizing, shortly ONC process of tool steels, done with our colleagues from Bulgaria. In our first study, ONC process was applied onto four different tool steels. Their chemical composition and preliminary heat treatment procedure are shown on the left side table. In the figure at the right-hand side, their heating and gas pressure regimes during vacuum ONC process conditions are given. Before these experiments, some phase diagram calculations were performed by using advanced phase diagram module of FactSage. Iron carbon nitrogen interaction was important to simply understand the ONC process. So in the first figure, we calculated iron nitrogen carbon ternary phase diagram to estimate the possible reaction products during our experimental process, which has both nitriding and carburizing potentials with a gas mixture of ammonia and carbon dioxide at zero point 0.8 bar and 570 degrees Celsius. In the second figure, we simply calculated the oxidation behavior of a carbonitride layer, the epsilon phase in such system. It is known that the nitrogen and carbon atoms do not only interact with the iron but also alloying elements forming a surface, compound, and underlying diffusion layers. So we have decided to add main alloying elements to the simple iron carbon nitrogen system. For example, the first figure shows the effect of chromium with 5 weight percent, and the second one shows the effect of tungsten with 8 weight percent, and the third one shows the effect of molybdenum with 3 weight percent to this system. As can be seen that the alloying elements in the steels has great effect on the formation of different layers during ONC process. The instrumental analysis were also performed for detailed characterization of the samples. We can conclude that the agreement of the model results with the analysis proved the importance of the model study. Another study was done with collaboration of Asil Çelik, that is one of the alloyed steel producer in Turkey. In the present study, we aim to minimize the nozzle clogging while controlling the inclusion morphology by calcium treatment. We carried out a modeling study and industrial practice for calcium treatment process of a selected aluminum killed steel grade with a sulfur addition. For this aim, first thermochemical calculations were performed by FactSage to calculate the required amount of calcium silicon wire to prevent the nozzle clogging and to predict the evolution of inclusions after calcium treatment. Then, an industrial trial was carried out for the selected steel grade. As you know, calcium treatment process for aluminum killed steels is mainly used during secondary metallurgy operation with two main objectives. To improve the castability, to minimize the nozzle clogging, and to modify the shapes of the sulfide inclusions. Adding proper amount of calcium to obtain the right composition for the inclusions is very important. Insufficient or excessive calcium treatment may be even more detrimental to the steel castability. This animation shows what happens once we inject a calcium wire to the molten steel in the ladle. Some portion of the calcium will evaporate from the surface of the melt. Some of the calcium dissolved in the steel and remains as an oxide and sulfide inclusions. Some of these inclusions float up to the steel slag layering time. What we are looking for in the calcium treatment is the total amount of retained calcium in the steel. Here you see the trial road. Wire additions were done after vacuum degassing and before tarnish operation. During trials, steel lollipops and slag samples, as well as temperature dissolved oxygen measurements, were taken at the different points throughout the process. Here you see a binary calcium oxide alumina phase diagram calculated by FactSage. This diagram is one of the mostly used tools to understand the calcium treatment process, just looking at the deep eutectic point between the calcium aluminide cliffs. One easily calculates the amount of calcium wire required for liquid calcium oxide alumina formation, just looking at the phase diagram when insoluble aluminum and calcium concentration in steel are known. Especially when steel contains a certain amount of magnesium, this ternary phase diagram will be more accurate to estimate the type of the oxide inclusions compared to binary phase diagram. By the way, the aim is same to add proper amount of calcium to obtain liquid inclusions in the melt. However, those diagrams present only a simplistic approach, since it is not sufficient enough to simulate a real level operation, especially when other ingredients are taken into account in the molten steel, such as sulfur, silicon, titanium, magnesium, oxygen, manganese, etc. We know that calcium content in high sulfur containing steels should be limited to avoid precipitation of solid calcium sulfide, which bring a nozzle clogging problem too. Here you see that the figure shows the inclusion diagram for the iron, sulfur, aluminum, calcium, oxygen system at 1600 degrees Celsius. In this calculation, as you seen in the graph, sulfur is 200 ppm, aluminum is 400 ppm, y-axis is the total calcium and x-axis is total oxygen in ppm. As can be seen, blue colored area, which is also called slag window, where all the inclusions are liquid, and this area is narrow due to the solid calcium sulfide and calcium aluminate formations at different calcium and oxygen levels. As the graph shows, when sulfur is included in the system, we have to work in very narrow space. Here you see another calculation with FactSage about the phase change of oxide and sulfide inclusions during solidification after calcium treatment. The liquid inclusions disappear as the temperature drops. Manganese sulfide and calcium sulfide start to form below around 1540 degrees Celsius. In addition, calcium aluminate and calcium magnesium aluminate formation occur upon cooling. Thermochemical modeling was also carried out to estimate the required amount of calcium silicon wire to prevent the nozzle clogging for our trial. The selection of proper databases for a given system was essential for accurate thermodynamic calculations. For this calculation, the measured chemical composition of selected steel just before entering the calcium station was used as an input parameter. Although spinel formation cannot be avoided, it can be decreased to minimum levels with calcium addition. For the optimum calcium addition, we aim to add sufficient amount of calcium silicon wire which forms minimum solid calcium sulfide and spinel inclusions but maximum liquid inclusions, where it is seen with the blue line on the graph. Some investigations were performed from the lollipop samples to see the morphology and chemical analysis of inclusions. Oxysulfide and oxide type inclusions in the samples were detected in terms of size and composition distribution and displayed in these ternary plots. and statistical results were plotted to the inclusion distribution graph. It can be concluded that, according to these investigations, the practical findings could be explained by the results of the model calculations. Our third and last case is about an ongoing project entitled Development and Additive Manufacturing of Oxide Dispersion Strengthened, ODS, Inconel 718. The team leader of the project is my colleague Eda Aydoğan from Middle East Technical University, and the other collaborators are from Los Alamos National Lab, Oak Ridge National Lab, and Sabancı University. As it is known, Inconel 718 has superior mechanical properties, thus it is widely used for elevated temperature applications such as gas turbines, turbocharger rotors, and nuclear reactors. However, above 700 degrees Celsius, sudden decrease in mechanical properties of the alloy is reported in the literature due to the particle growth and lack of stability of the strengthening precipitates. So, why the research group has decided to use nano-oxides? There are some successive studies in the literature that the oxide dispersion strengthened ODS alloys have been shown to exhibit outstanding stability at much higher temperatures due to the existence of nano-oxide particles, which are reported to be mostly yttria titanium oxide or yttria aluminum oxide or hafnium titanium oxide systems. Why selective laser melting process? Because these alloys are hard to process with the conventional techniques, and these techniques reduces the production times of ODS alloys and results in homogeneously distributed particles. In the study, prior to experimental work, first we created equilibrium, non-equilibrium, and Scheil-Gulliver calculations by FactSage to predict the phase of the Inconel 718 alloy upon cooling and to estimate the possible heat treatment temperature range of the ODS alloy. Metastable gamma double prime phase added to the non-equilibrium calculations from MatCalc Open Database. We wanted to predict what happens if we add different elements or oxide such as yttrium, yttria, hafnium, hafnia, titanium to obtain nano-sized ternary oxides in the alloys like yttrium titanium oxide, hafnium yttria oxide, etc., which provides ODS effect. However, none of commercial database of FactSage had the thermochemical data to estimate such ternary oxides, but the Ab initio materials project database from GTT. I know that now there is one more option named Open Quantum Materials Database again from GTT. Anyway, we created many calculations. Here you see just some examples. We tried to estimate the most suitable additions and the amounts for obtaining the desired ternary nano-oxides. According to our calculations, we realized that in addition to these additives, the amount of oxygen within the alloy was also crucial to form these nano-oxides. The important aspect was how to add these additional oxygen before the additive manufacturing process. We thought that we could achieve this by adding oxygen sources such as iron oxide, cobalt oxide, and nickel oxide to the initial powder mixture just before selective laser melting process. The first graph, for example, shows the effect of oxygen on ternary oxide formation, and the second shows the effect of iron oxide for the same manner. Then we decided to use the phase diagram module to find the most suitable triple oxide formations just by scanning the wide range. As an example, the first figure shows effect of both oxygen and yttria. uh, whereas the second one shows the effect of both iron oxide and yttria in inconel alloy at 700 degrees Celsius to estimate the formation of these special nanooxides. As a result, the FactSage calculations were found in agreement with the microstructural analysis of the samples, and most importantly, ab initio database from GTT helped us to estimate the yttrium and hafnium containing multi-component oxide particles formed in as built or following heat-treated ODS alloy samples. As a conclusion, we use FactSage effectively for more than 20 years for academic research studies and metallurgical courses, and it has proven to be an indispensable resource for our experimental and modeling investigations. And thank you so much for your listening.